So this video is on transformations and characteristics of parent functions. This is not all of the parent functions, this is just some more of them. We're going to study even more parent functions this year. So the next one we have is the square root function. You can see how each of the transformations works. We can see the a value is still doing the stretch and compression like we're used to. So I'm not going to write out everything the way that we've been doing in the other notes. I'm just going to remind you what it is. Stretch, compression, and reflect over x. The h is going to be left and right. The k is going to be up and down. A square root x graph is going to be a little bit different as far as what x values we plug in. So normally we would plug in -2, -1, 0, 1, and 2, but we're thinking about numbers that we're going to square root, and square rooting numbers like 2 are not going to be great because those are hard to square root. That's a decimal. So I'm still going to have 0, I'm still going to have 1, but I'm going to pick a number to square root like 4. 4 is easy to square root. And I'm actually going to put -1 and -4 just to have that symmetry, not because I'm going to get a value, because you guys might look at this and go, what, Miss Rice, you're crazy, you can't square root a negative number. So over here, the square root of -4 is undefined. We know that, undefined. The square root of -1 is undefined. So I just plugged those in just to show that we can try to plug in negative numbers, but it's not going to give us anything. The square root of 0 is 0. The square root of 1 is 1. And then the square root of 4 is 2. We have the point 0, 0. We have the point 1, 1. And we have the point 4, 2. So a square root graph looks like this. It is, I always think of it as half of a sideways parabola. All right, so there's our square root graph. Given y equals negative square root x plus 5 minus 7, find the transformations and the locator point. So here we're not going to call it a vertex, we're going to call it a locator point. And just like before, the h and the k are going to help us find the locator point, kind of what we think of as the vertex. So it's going to be this point. Find the transformations on the locator point and then graph the function. So here, instead of having 5 points for our transformations, we're only going to use these 3. Miss Rice, do I have to memorize them? No, just like before, you're going to think of what numbers to plug in if you ever forget. You're going to think of what numbers you could plug into this parent function, and then you can transform those points, all right? So I'm going to list the transformations. I have reflect over x, left 5, and down 7. And then I'm not going to use my undefined points because that's kind of silly. I'm just going to use 0, 0, 1, 1, and 4, 2. And so I'm going to reflect over the x-axis. That means I'm going to take my y-coordinates and multiply them by -1. Then I'll go ahead and take my points and shift them to the left 5, left 5, left 5, left 5. And then I'll take my points and shift them down 7, down 7, down 7, down 7. So I have the point -5, -7, -4, -8, -1, -9, and so there is my graph. And the locator point you can see from the graph, but we can also see it from the equation. The locator point, kind of what we used to think of as the vertex, is -5, -5, -7. If you call it the vertex, am I going to get upset? No. I'm just going to tell you, oh, it's a locator point in this problem, in this context. Okay, so cubic, very, very similar looking to a quadratic or a parabola. The only difference is the exponent is a 3 instead of a 2. So again, the a in the front is a stretch, TCH, or a compression, or a reflect over x. The H is a left or right shift. The K will shift it up or down. This one again is going to have a locator point instead of having a vertex, and that is going to be HK. For a cubic graph, we can just use the points -2 to 2 for the x values, -2, -1, 0, 1, and 2. Those are pretty easy to plug in because you're just taking the number and multiplying it by itself 3 times. So -2 times -2 times -2 is -8. -1 times -1 times -1 is -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So for each of these numbers, we were just plugging it into the parent function, which means we were multiplying it by itself 3 times. We were cubing each number. So I'm going to go ahead and plot the points. -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. So when I draw this parent function, I like to think of it as like half of a parabola going up and half of a parabola going down. So here's my parabola half going up. There's my parabola half going down. All right. To keep the video from getting too long, I'm going to say let's go ahead and do this example in class tomorrow. Next is a cube root. The part that is going to feel so strange about this is that it's going to be kind of similar to square roots, but you can cube root a negative. So for this, we're going to pick numbers that are easy to cube root, and the numbers that are easy to cube root are the numbers that we just used. So it's easy to cube root a -8. It's easy to cube root a -1. It's easy to cube root 0. It's easy to cube root 1. It's easy to cube root 8. So there's a little bit of strategy involved when we come up with our tables for our square root and our cube root. There's a little bit of strategy. Okay, so when you cube root a number, you are thinking what multiplied by itself 3 times gives you -8. And so the number multiplied by itself 3 times that gives you -8 is -2. So the cube root of -8 is -2. What multiplied by itself 3 times gives you -1? Well, it's -1. What multiplied by itself 3 times gives you 0? Well, it was 0. What multiplied by itself 3 times gave us 1? It was 1. What multiplied by itself 3 times was 8? Well, that was 2. So the cube root of 0 is 0, the cube root of 1 is 1, the cube root of 8 is 2. That's kind of how you read those, all right? So again, these transformations, I couldn't think of the word, they mean the same thing here. So we got our stretch, we got our compression, we got our reflect over x, we got our left and right shift, we got our up and down shift. Again, we have what we're going to call a locator point, technically not a vertex, but essentially what we think of as a vertex. And this graph is going to look very similar to the way the cubic graph looked. We plot the point -8, -2, -1, -1, 0, 0, 1, 1, and then +8, +2. So kind of like parabolas on its side, but half and half. So half a parabola on its side, and then another half of a parabola on its side. That's how I think of these. Okay. Again, I will let us practice these, drawing these two in class. So go ahead and turn to the next page of your notes. All right, so just like last time, I left these typed out for us. So let's go ahead and find the locator point of example 4. So the locator point here is -1, -3. So it's the opposite of the number inside. Just like with the transformations, we think of it as the opposite of whatever that transformation is doing for the inside, and then exactly the same as the number outside. Domain and range for these problems gets a little bit more interesting. Not so much with this one. This is a cube root graph. For the square root graphs, it definitely would have been more interesting. And we can get to one of those tomorrow in class. So for this one, domain, the arrow goes left forever and right forever. So domain, if you guys recall, is the x values, left forever and right forever. So this one, the domain is going to be -infinity to +infinity. For this one, the same thing is going to happen for the range. This graph goes down forever and up forever. So those arrows, not only do they go left and right, but they also go down and up, which tells us that the range and the domain happen to be the same on these graphs. So those particular graphs for domain and range are kind of boring. All right. Increasing interval and decreasing interval. If you guys recall, I do have a typo right here, which I need to go back and fix. Increasing and decreasing interval is always based off of your x values, never your y values, always x values. So here, if I put my stick figure right here, now this one is really interesting. We haven't seen a case like this before. Usually we have an arrow. This graph just stops. It stops right there. And you can figure out that x value because it is the locator point. It is stopping right there at the locator point. The locator point for this problem is +3, +6. And since we are doing an increasing or decreasing interval, we are only using the x coordinates, which means we are only using 3. So 3, and then it's a right arrow. We're using x values. It's a right arrow, so that's a +infinity. And if I think about what my stick figure is doing, he is walking downhill a little bit, so he is decreasing. So for increasing interval, I would write none. And for decreasing interval, I would write 3 to infinity. To infinity. All right. For maximum and minimum, now we are going to get a little bit more specific on these graphs for maximum and minimum. I went ahead and I added this on these notes. If you compare this to last unit's notes, it did not say this. When we look for maximums, go ahead and circle this, and if you have a highlighter, highlight it. Maximums only happen with something that looks like a mountaintop, and they cannot be endpoints and they cannot be arrows. They have to look like mountaintops. Minimums have to look like valleys. They cannot be endpoints, they cannot be arrows. So if we do not see something in the picture that looks like a mountaintop or that looks like a valley, then we don't have a maximum, we don't have a minimum. If you look at this example, for example 6, I don't see something that looks like a mountaintop, I don't see something that looks like a valley. So this is interesting compared to what we've dealt with before, and that we don't have a maximum, we don't have a minimum. So I'm going to say none for both. None, none. All right, next page. All right, x-intercepts and y-intercepts. Just like before, we're going to find these with our calculators. I'm going to go ahead and write out the steps just like before. You're going to put these in your notes. So the steps, the calculator steps for x-intercept is second, trace, number, 2. That's because another word for x-intercept is the 0 of the graph. The reason is that the y-coordinate is always 0. The y value is also called the function. Y equals the equation, so y is also called the function. When the function equals 0, that's when the graph equals 0. So they call them the zeros of the graph. For the y-intercept, we're going to do second trace. Option number 1, and we're going to set the x-coordinate equal to 0. So that's the way that we do this in a calculator. I'm going to go ahead and get my calculator out and do that now. If you have a calculator at home, I would like you to do that with me. So, sorry, pause. Okay, let me go ahead and type this in. I'm going to actually show you guys something here. So I'm typing 1/3, and I'm typing this in as a fraction. 1/3 x plus 2 to the 3rd plus 1. I'm going to go ahead and hit graph. All right, so I'm going to go ahead and do second trace. Option number 2, I'm looking for my x-intercept. I can see my intercept is somewhere around -4, so I'm going to tell my graph, I don't know, do my left bound is -10. I'm going to do my right bound is 0. My x-intercept is somewhere between -10 and 0. So my x-intercept is -3.442. So the last time I made a video, I showed you guys how to find the x-intercept when we were being really specific. We were saying like, oh, it's between -4 and -3. But you can actually be as general as saying, oh, the x-intercept is between -10 and 0, and your graph will still find it. Okay, let's do the y-intercept. Second trace, option number 1, plug in 0. Now, it gave me the y-intercept as a fraction, 11/3, because I typed a fraction right here. Now, if you don't like your answers being fractions, what you can do is at the end of your equation, this is a special calculator trick that I learned, at the end of your equation, you can hit the math button right here, and you can go down here to number 2 and say, whatever outputs I get, I want you to turn them into decimal form. If you don't like fractions, have it turn your answers into decimal form. Now I can go back and hit second trace, option number 1. I can say plug in 0 to give me my y-intercept, and now it's going to give me my y-intercept as a decimal. So that's just a neat little trick if you do not like to get your numbers as fractions. Of course, the fraction form would have been fine. All right. Next, continuity. Whether the graph is continuous, a continuous curve you can trace. Goodness gracious, I could not read that. So continuity is where you guys, I'm going to leave this here. It's an imperfection in the video, which adds character. So a graph is continuous if you can trace it with your finger without picking up your finger. I just wanted to describe that. So my note was quadratic functions are always continuous. We're going to add a note to that. So are cube root, square root, and cubic. All of those graphs that are in this video, they are all continuous. So we have not yet gotten to graphs that are interesting and that they are not continuous. We're still on the graphs that are kind of like boring continuous. All right, let's go ahead and do the end behavior. I've got 2 examples of end behavior here. I didn't want to be exhaustive and give all the examples because that would have been just too many examples, and I figured we could just do a couple and use that to help us with the other ones. So as you guys recall, we always do the left arrow and the right arrow. So as x goes to -infinity, as x goes to +infinity, we want to say if the arrow is going up or down. So for my left arrow, I can see that the arrow is going down. As I look at the right arrow, I can see that the arrow is going up. It's not going up very fast, but it is going up. Okay. Now this one is the funkiest one of all, and for the whole year, it's probably the funkiest one we're ever going to see, to be honest. So this one I'm going to say, let's look at the left arrow, and you might be saying this, Rice, there is no left arrow, and yes, that is exactly what makes it funky. So as we look at the left arrow, there isn't one. So we're going to say, as we look at the left arrow, it is undefined. There's nothing there. Okay, as we look at the left arrow, it is undefined. The arrow's not going up, it's not going down, it's just not there, it's imaginary, it's invisible. And then this one, as we look at the right arrow is going down. All right, so that is it for the notes. We will finish filling out the notes tomorrow in class. I apologize again for the imperfections. They're not bad enough for me to re-record the video, so I'm gonna leave it. Sorry guys, sorry.